Welcome back to Mechanical Engineering Made Simple.
It's great to be back.
Today we have a mission, and that mission is to move way, way beyond the basic container. When most people think of a pressure vessel or a tank, they just think of a big steel can holding some stuff.
Right. Maybe it's gas, maybe it's liquid. It just sits there.
It sits there, it does its job, end of story.
Which is, that's the most boring part of the design, really.
Yeah.
If you're just designing a perfect cylinder to hold pressure, you could do that on the back of a napkin.
Exactly. We are ignoring the boring parts. Today, we are looking at what happens when you decide to punch giant holes in that pressure vessel. What happens when you strap a vibrating motor to it? Or you fill it with solids that act like arches, or you heat it up until the steel is screaming to expand, but the concrete lining inside says, absolutely not.
It's a messy, chaotic world inside those tanks.
And to navigate this mess, we are tearing through a stack of documents from the Pressure Vessel Design Manual. We're talking chapters on large openings, special designs, local loads, the really gritty stuff.
And if we had to put a theme on this deep dive, it would be discontinuity and stress. You see, a perfect, uninterrupted cylinder is easy to calculate.
Right.
The math is beautiful and simple because the stress flows evenly, like water in a smooth pipe. But real engineering happens at the interruptions, the nozzles, the supports, the interfaces where materials are fighting each other.
That's where the stress concentrates.
That's where things fail.
So let's start with the most obvious way to ruin a perfect cylinder. You cut a hole in it.
The Swiss cheese problem, yeah.
Right. Now, my intuition says, okay, I cut a hole to put a pipe in. I just need to patch it up with enough metal to replace what I removed.
Like area replacement, right?
That is the old school way of thinking, and it gets you into trouble fast. It is much more complicated because you are dealing with two completely different types of stress now.
You have the membrane stress, and then you have the bending stress.
Break that down for us, because membrane just makes me think of a balloon.
That is actually a perfect analogy. Imagine a balloon. The skin is being stretched evenly in all directions. That's membrane stress. It's uniform.
Sure.
But now, imagine you take a rigid plastic straw and glue it to the side of that balloon, and then you pull on the straw.
You're creating a leverage point. You aren't just stretching the skin anymore, you're trying to snap it.
Exactly. That is bending stress. The nozzle acts like a lever arm. It creates a moment. It's flexing about what we call the hard axis. The manual breaks this analysis down into specific cases for large openings.
And the math is pretty strict here.
Very. You have to check that your membrane stress, let's call it sigma m, is less than your allowable stress, S. That's step one.
Okay, so the stretching part has to be safe.
Right. But then you have to check the combined stress, sigma m plus sigma b, the membrane, plus the bending. And the code says that total has to be less than 1.5 times S.
Wait, 1.5 times? That seems generous.
Yeah.
Usually engineering codes are conservative. Why are they letting us go 50% over the allowable stress?
It's because of the nature of bending versus stretching. You see, if you overload a membrane in tension, it rips. Catastrophic failure.
Or it just tears.
But bending is different. The outer fibers of the metal might yield, they might stretch permanently, but the inner fibers are still holding strong. This is what we call the plastic hinge or plasticity reserve.
Ah.
The code is basically saying, we know it's going to bend and we'll allow the surface to yield a little bit locally to redistribute the load, but don't go crazy.
That makes sense. It's the difference between snapping a rubber band and bending a paperclip. The paperclip bends but doesn't break immediately.
Precisely.
Yeah.
Now, if you exceed those limits, you have to reinforce it. You need a reinforcing pad. But this is where I see engineers get it wrong constantly.
They just slap on more metal.
They think, I have high stress, I'll just slap a massive 3-inch thick steel plate on it.
More metal is better, right?
Wrong. The manual brings up the 2/3 rule and some other limits. It's surprisingly picky. It basically says the pad shouldn't be thinner than 0.75 times the shell thickness, but also, and this is key, not thicker than 1.5 times the shell thickness.
Why limit the thickness? Why can't I make it super strong?
Compatibility. Think about that balloon again. If you glue a thick, rigid steel washer to a soft rubber balloon, what happens at the edge of the washer when you inflate the balloon?
Oh, it tears right at the edge because the balloon is stretching and the washer isn't.
Exactly. If your reinforcement is too thick compared to the shell, it becomes a rigid hard point. It refuses to flex. So instead of distributing the stress, it concentrates all of it right at the toe of the weld.
So you crack the vessel because you made the patch too strong.
You did. You want the reinforcement to breathe with the vessel, not fight against it.
So it's the Goldilocks zone of steel plates. Not too thin, not too thick. It has to move with the system. Now, speaking of things moving, let's talk about the wobble.
Vibration.
Specifically, tall, skinny towers. The source material paints this terrifying picture of a tower just sitting there in the wind. And it's not that the wind is blowing it over like a tree. It's something sneakier.
Vortex shedding. This is a critical concept for anything tall and cylindrical. As wind flows around a cylinder, it doesn't just flow smoothly past, it splits. And as it rejoins on the backside, it creates these low-pressure swirls, vortices.
Like the wake behind a boat.
Similar. But these detach in a rhythm.
Mm-hmm.
Left, then right, then left.
Yeah.
It creates an alternating force sideways to the wind direction.
And if that rhythm matches the tower's natural sway?
You get resonance. The tower starts to oscillate. We call this the critical wind velocity. It's like pushing a kid on a swing. If you time the push perfectly, they go higher and higher.
The forces just magnify.
Incredibly fast.
So how do we stop the wobble? The manual suggests stiffening rings. I pictured these like the ribs in a human skeleton.
That's a good analogy. They add stiffness to the shell to break up that vibration mode. Basically, they change the natural frequency so the wind can't catch it anymore.
But sticking with our theme of discontinuity.
There's always a price.
There always is.
The shell wants to flex under the wind load. It wants to ovalize or bend. The ring says no. So immediately adjacent to that ring, you get a massive spike in longitudinal bending stress.
Ah, so you fix the global problem, the swaying, but you create a local problem.
Exactly. Stress at the ring attachment.
And we have to worry about how much it sways, too. The rule of thumb mentioned was limiting deflection to 6 inches per 100 feet of height.
Which is actually quite a bit of movement. Imagine standing on top of a 10-story building and it swaying 6 inches side to side.
No, thank you.
But the calculation for that deflection really highlights why height is so dangerous. The formula for deflection involves the weight, W, and the length, L, raised to the 4th power.
Okay, stop there. L to the 4th power. I want to make sure everyone catches the implication of that exponent.
It is the most sensitive variable in the equation. It means if you double the height of your tower, you go from 50 feet to 100 feet, you don't double the deflection.
You don't even quadruple it.
No.
2 to the 4th power is 16.
Correct. You increase the deflection by 16 times. You make the tower twice as tall and it becomes 16 times as wobbly.
That is terrifying leverage. That explains why making things just a little bit taller is an engineering nightmare.
It explodes the requirements for stiffness. You are fighting an exponential curve.
Okay, so we've got wind pushing from the outside. Now let's look at the war happening inside the walls. I want to talk about refractory linings.
The battle of materials.
This sounds like a recipe for disaster. You have a steel shell, which we know loves to expand when it gets hot.
And you line the inside with refractory concrete, which is basically ceramic, and it hates expanding.
And you bond them together and heat them to 1,000 degrees. What actually happens mechanically when you turn up the heat?
Well, the steel shell heats up and expands outward. The hot face, the inside surface of the concrete directly touching the fire, wants to expand the most. But the outer concrete is cooler. So during operation, the hot concrete is pushing against itself. It's in compression.
And concrete loves compression. It's happy there.
It thrives in it. But the problem isn't heating up. The problem is shut down.
The cooling phase.
Exactly. Imagine you cut the heat. The steel shell cools down and contracts. It shrinks like a belt tightening around a waist.
Uh-huh.
At the same time, the inside surface of the concrete cools rapidly and shrinks. Since the rest of the material is holding it back, that interface goes into tension. It's being pulled apart.
And concrete hates tension.
It has almost zero tolerance for it. That is when you get cracks. The source material mentions checking the modulus of rupture. The design rule is that the allowable tensile stress is roughly 40% of the modulus of rupture at 1,000 degrees. If you exceed that, the lining snaps.
You can actually hear it.
Sometimes, yeah, loud pops inside the vessel as the liner cracks.
That's unnerving. But there was one concept here that blew my mind. Creep. Usually when I hear creep in engineering, it's a bad thing. But here, the manual acts like creep is the hero.
In this specific context, yes, creep is usually the villain. But in refractory linings, it's a saving grace. At high temperatures and high compressive stress, the refractory material essentially relaxes. It slowly flows or deforms over time to relieve that internal stress.
So it's basically stress relief yoga for the concrete.
In a way, yes. The manual notes something counterintuitive. The creep rate allows the material to survive the thermal cycle. Without creep, The stress would build up like a loaded spring until the material shattered. Creep dissipates that energy.
Amazing. The material sacrifices its shape slightly to save its structural integrity. Okay, moving from heat to motion, let's talk about agitators. We are turning this pressure vessel into a giant blender.
A very violent blender.
I always thought you put a propeller in a tank, you spin it, you mix the fluid, done, simple.
That is the common misconception. If you put a paddle in a smooth, round tank and spin it, you don't get mixing. You get swirling.
The liquid just spins with the paddle.
Yeah.
A lazy river.
Exactly. The whole liquid mass acts like a solid flywheel. The liquid is moving at almost the same speed as the impeller. If there's no speed difference, there's no shear.
And no shear means no mixing.
You're just taking the ingredients for a ride.
So how do we fix it? How do we break the lazy river?
Baffles. You weld vertical metal strips to the side of the vessel walls.
Those little fins sticking out.
They look insignificant, but they are doing the heavy lifting. They act as a brake. They stop the fluid from spinning and force it to turn, over-converting that rotational energy into vertical pumping and turbulence. That chaos is where the mixing happens.
But if you're stopping thousands of gallons of spinning liquid, those baffles must be taking a beating.
Massive forces. You are essentially slamming a river into a wall. The manual has a specific formula for the force on a baffle. Depends on the horsepower and the impeller RPM. Let's call it N.
I looked at that formula. It was force equals a constant times horsepower divided by RPM.
Right. And look at the relationship. Horsepower is on top, RPM is on the bottom.
So if I lower the RPM, the force goes up. That feels backwards. Shouldn't a faster mixer hit harder?
Think about torque. If you have a motor with the same horsepower, but you gear it down to run slow, it produces massive torque, like a tractor in low gear.
Oh, okay.
That torque is getting transferred to the fluid, and the fluid transfers it to the baffle. So a slow, sludge-churning mixer exerts way more force on the tank internals than a high-speed propeller.
That is a gotcha moment. You could design a tank for a fast mixer, then someone swaps in a slow, high-torque mixer, and suddenly, rip, the baffles are torn right off the wall.
Happens more often than you'd think.
Speaking of things behaving counterintuitively, this was my biggest aha moment in this depth dive. Bins and silos.
Ah, yes. Where intuition goes to die.
Seriously, I looked at this section and thought, why is this even here? If I fill a tank with wheat or coal, isn't it just like filling it with heavy water? And the manual screams, no.
It is definitely not a liquid. Solids have friction. They have internal shear strength. They arch or bridge.
The source references the Lambert and Ketchum theories. Can you break that down? How is a silo different from a water tank?
In a water tank, the pressure on the bottom is simple. It's the total weight of the water. 100 tons of water, the floor holds 100 tons.
Okay, standard physics.
But in a silo, the grain wedges against the sidewalls. Friction locks it in place. We call it arching. The material creates internal arches that push against the walls. This means the walls end up supporting a huge portion of the vertical weight.
So the floor doesn't feel the full weight?
No. The pressure on the bottom is significantly less than the total weight of the material. The manual shows the pressure curve flattening out. After a certain depth, the pressure on the floor stops increasing entirely.
That sounds like a good thing. Less load on the foundation.
It sounds good for the floor, but it's dangerous for the walls. Because that load didn't disappear, it moved. It went into the walls as a vertical compressive load.
So it's pulling the walls down.
Yes. The friction creates a drag force. You can actually crumple the silo like an empty soda can because the friction of the grain is dragging the steel walls down towards the ground.
That is a wild image. A steel tower crumpling vertically because the corn inside is grabbing onto it.
And then there's the flow, the angle of repose. Wheat on steel slides differently than coal on concrete.
This determines if the stuff actually comes out, right?
Right. If you get the friction coefficients wrong, the material won't flow. It forms a rat hole, a tunnel straight up the middle, and the rest stays stuck. Or worse, it flows unevenly.
And that creates an eccentric load.
Exactly. The center of gravity shifts, and the silo can literally tip over.
It's fascinating that sand and water, which look similar, behave so completely differently in a tank.
It's all about the shear strength. Liquids have none. Solids have plenty.
All right, we have time for one last section. The coolest shapes. Spheres and coils. First off, spheres. Why don't we build everything as a sphere?
Geometric efficiency. A sphere is the strongest shape for holding pressure. It distributes stress perfectly evenly. But they are a nightmare to build in the field.
The manual talked about the orange peel method.
Yes, forming steel plates into tapered segments like an orange peel. or the soccer ball method. But think about the fabrication. You are welding curved plates high in the air, and then the hardest part, you have to hold it up.
Gravity is the problem.
Always. You can't just set a sphere on the ground, you need legs. But attaching a vertical straight leg to a curved spherical shell is a geometric mismatch. It's a discontinuity.
If the leg wants to go straight up, the shell curves away.
Exactly. When you put weight on those legs, they try to punch through the shell. You get massive local stresses right at the attachment points.
So the sphere is perfect for pressure, but terrible for gravity. Now, inside these vessels, we sometimes put pipe coils for heating or cooling. And you found a detail here that creates a very specific type of flow.
The double eddy effect, or the Dean effect. This is fluid dynamics at its finest.
Walk us through it.
Okay, when water flows through a straight pipe, it's lazy. The water in the middle moves fast, the water near the walls moves slow.
Right.
But when you curve that pipe into a coil, centrifugal force kicks in. The faster-moving water in the center of the pipe gets thrown to the outside of the curve.
Like a car taking a turn.
But the water has to go somewhere. So it hits the outside wall, splits, travels along the walls back to the inside of the curve, and pushes into the center again. It creates two counter-rotating swirls inside the tube.
So the water spirals while it flows?
Yes. It's turning itself inside out constantly.
Mm-hmm.
And that turbulence is fantastic for heat transfer. In a coil, the Dean effect constantly mixes the hot and cold fluid. It scrubs the heat off the walls.
So you get much better efficiency just by bending the pipe.
You do. You pay for it in friction, you need a bigger pump. But for a heat exchanger, it's brilliant.
It's amazing how much complexity is hidden inside a curved pipe.
It really is.
So let's unpack this entire deep dive. We started with a simple cylinder. But by the time we're done, we've got a system where the wind is trying to shake it apart with vortices.
The internal mixer is trying to shear the baffles off the wall with low-speed torque.
The heat is trying to crack the lining through differential expansion.
And if it's a silo, the friction of the contents is trying to crush the walls vertically like a soda can.
A pressure vessel isn't just a container. It's a battlefield of forces.
It is a complex system of conflicting requirements. You solve one problem, like adding a stiffener for wind, and you create a new problem like local stress concentrations. Design is about balancing those conflicts.
And that leads us to the final thought. What's the one thing you want the listener to take away from this?
For me, it's the concept of scale and the reality of field fabrication. We aren't talking about precision lab equipment here. We are talking about massive structures built outdoors in the mud by guys with welders.
Right, it's not a watch, it's a monument.
Think about the thermal calculations we discussed. If you are off by a single degree in your thermal expansion calculation on a 300-foot tower, that translates to inches of steel moving where it shouldn't.
Inches.
Inches. In a rigid metal structure, a movement of 1 inch is catastrophic. It shears bolts, it buckles supports, it rips piping flanges apart. The math we look at on paper, the sigmas and the deltas, they represent massive physical forces.
That is a sobering thought. The math is real and the consequences are heavy.
Absolutely. If you respect the discontinuities, you'll be fine. If you ignore them, they will find you.
Well, that is all the time we have for today's deep dive into the crunch of metal and the flow of stress.
It was a pleasure.
If you haven't already, get over to our YouTube channel, Mechanical Engineering Made Simple, where we post hands-on how-to videos, visual breakdowns, and practical engineering walkthroughs you can actually use. A family that solves together stays together.